Hi everybody, welcome to the session. Today I'm going to be taking you through architecting explainable AI decision support on FHIR. My name is John Grimes and I'm from CSIRO, Australia's National Science Agency. My job is to research new tools and techniques at the intersection of analytics and health data standards. I'm the lead on a project called Pathling that provides tools for transforming FHIR data at scale using Apache Spark. I'm also part of the group working on the SQL on FHIR standard. The way I'm going to structure this talk is to first provide some background on AI-based decision support in healthcare and some of the challenges that exist in this space. Then I'll establish some principles that we can use to create thoughtful solution designs in this area. Next, we'll look at some of the relevant standards that can be leveraged. And finally, we'll go through some patterns and examples that illustrate their use. Decision support in healthcare has a long history that includes many clinical and operational applications, including diagnosis, prescribing, alerting, and patient flow management. The use of AI within healthcare is not new, but AI models are getting more capable in ways that matter. The application of AI within the health context is an area of acute interest right now. There remain challenges in translating AI decision support into frontline care, some of which relates to trust and alignment, but also practical considerations such as integrating with existing systems and scaling the use of the technology. We want decision support tools to be able to connect to EMR systems so that clinicians can integrate them into their existing workflow. We also want to be able to use standard interfaces to connect these tools so that we can reuse these integrations across different systems in different locations. We want the freedom to substitute and adapt decision support solutions according to the needs of the business. We need architectural patterns that can guide new implementations to be built out in a sustainable and extensible way. We should be aiming to maximize the encapsulation of our decision support solutions, limiting any dependencies that other components might have on the internal implementation details of the service. For example, we should not have to re-engineer the integration if the service changed from a rules-based method implemented in Java to a deep neural network driven by a Python script. A standard interface for the inputs and outputs of the service can be designed to be agnostic of these types of details. The decision support service should be able to be reused across multiple different deployment contexts. This might be different EMR products, it could be across multiple healthcare facilities or both. The interface between the decision support service and the EMR software should be vendor agnostic and based upon open standards. This minimizes the cost of substitution and ensures that solutions remain closely aligned to business requirements. Finally, decision support services should be composable. They should be able to be combined, using their standard interfaces to create more complex systems. An example of this might be the use of a service to calculate a comorbidity index as an input for another service that predicts the risk of rehospitalization. The FHIR family of standards gives us a great set of tools to achieve these goals. The base FHIR standard gives us a way to represent our clinical and operational data and an API that can be used to query it at runtime to provide inputs for decision support. It also provides subscriptions to allow us to be notified of changes in real time. The bulk data access standard provides a way for data to be requested in bulk for training and evaluating decision support models. The Smart App Launch specification provides us with a way to create user interfaces to accompany our decision support services that can be launched from existing EMR systems. CDS Hooks provides a standard way for clinical systems to invoke decision support services and receive back structured actionable prompts. SQL on FHIR is a relatively new spec that provides a way of applying use case specific transformations to FHIR data for analytic purposes. It can be used to prepare FHIR data for import into a database or to extract training variables to be used as features in machine learning. If you're interested in hearing more about SMART, Josh Mandel is giving a talk at 4:45 right here. There are a couple of sessions relating to CDS hooks this afternoon in the Heritage Gallery from 4:45. And if you want to hear more about SQL on FHIR, tomorrow is the big day. There will be an intro session with Ryan Brush, Let's Build with Nikolai Rizhikov, and an implementation showcase. I'm now going to take you through several different patterns that support different decision support use cases. What all these patterns have in common is a reliance on 4 standard interfaces that serve as a gateway to data held within the health service. The first is a FHIR API, which can be used for querying and retrieving FHIR resources. It can also support pub/sub models through FHIR subscriptions. The second is the Smart Authorization endpoint. This interface is responsible for issuing tokens that can be used to access the other endpoints. The third is the FHIR Bulk Access endpoint. This interface can provide large amounts of FHIR data back in bulk format. Finally, a FHIR Terminology API can be provided to enable queries about the terminologies that are used within FHIR data produced by the health service. This can be important for the interpretation of codes within analytics and machine learning. In most cases, these interfaces will be implemented as some sort of proxy or harmonized view of the data and authorization model of the health service. This can be a lot of work to engineer, but the advantage of expending this effort is that we can then make these interfaces available for reuse. It can also reduce the overall complexity of the system by avoiding the need to develop and maintain a larger number of point-to-point integrations between components. Each use case will define a FHIR implementation guide. This is a set of expectations about the character of the data and how it can be accessed. This is the interface contract between the data platform and the applications and services that use it. The first example will be a clinical decision support service for predicting risk of rehospitalization. This service is used within the clinical workflow and is used to prompt the attending clinician upon opening the patient record that there is a high risk of rehospitalization, and the patient may be a good candidate for referral to interventions such as discharge planning and case management. The picture on the left is an example of a prompt that might be presented to the clinician. The picture on the right is an example of a user interface that serves to further explain the prediction. In this case, it is a visualization of the most important variables that contributed to the prediction that this patient will present back to hospital within the next 30 days. Now we'll talk about an approach to achieving this sort of user experience using standards. First, we'll cover the process by which the model itself is trained and evaluated using data from the health service. The initial training of the model can be performed using extracts provided by the FHIR Bulk Data Access API. The authorization token that is provided by the Smart Authorization endpoint can be scoped down so that only the data that is relevant to the training of the model is returned. The bulk FHIR data can be subsequently transformed into a flattened table using SQL on FHIR, containing just the predictor variables. The raw features are then persisted within a feature store. A feature store is a piece of infrastructure that is commonly used within MLOps architectures to share and reuse features, and also to store lineage information such as the source of the data and the piece of code that transformed it. In this case, we're linking a feature table to the SQL on FHIR view that created it. Feature engineering can be done to further transform these raw predictor variables into representations suitable for training. This is usually required to convert data into a numerical form required for machine learning. This process will be highly dependent upon the use case, and multiple versions of these features produced as part of the process of developing and improving the model. Some of this feature engineering may depend upon a FHIR Terminology API, which can be used to enrich coded data with additional information from the source terminology. If you'd like to learn more about this process, I'll be delivering a talk on Thursday called Using FHIR Terminology Within Data Analytics. The trained model will be evaluated against a held-out set of test data before it's deployed. However, once it has been deployed, it's essential to monitor its performance to ensure that it continues to provide high-quality results to the user. Here we are depicting a scenario where we periodically create new test sets as more data is collected and feed them into a process for measuring model drift relative to a previous baseline. Once the model's trained, we have a decision to make about how to deploy it and make it available to the EMR system it's designed to augment. Here we are describing how the CDS hook standard can be leveraged to provide a standard API for invoking the service and getting a result back. The EHR system sends a request to the decision support service that contains the details of the patient and encounter, along with the details of a FHIR server that can be queried for the necessary input data for prediction. The service then retrieves the data that it requires and executes its calculation. The result is returned as a set of cards. A suggestion describes the outcome of the operation, along with associated actions that can be taken. In this example, the action could be the creation of a service request for a discharge plan. The Smart App Link card provides a link that launches a smart app in context. This smart app may be capable of complementing the result or providing an interface to further query the data or perform common follow-up actions. In this example, it could be a visualization of an explanation of the result, such as the most important variables that contributed to the prediction. This diagram shows the hook service in the broader context of the other components that it depends upon and that depend on it. The EMR invokes the service, which uses the combination of FHIR data and the trained model to produce a result. The EMR then presents this result to the user. Included in the response is a link that can be used to launch our Explainability Smart App. And the Smart App can use both the FHIR API and the model to provide explainability for the prediction. Another example of decision support is an admissions prediction tool that uses historical encounter data to forecast admissions into the future. This is different to the rehospitalization example, as it is operational decision support that provides predictions that cover the scope of an entire facility rather than an individual patient or encounter. In this example, we want to provide a dashboard to users that shows the forecasted admission and separation numbers for the next week so that staff can plan and allocate resources effectively. As with the previous example, the initial training of the model is performed using extracts from the FHIR Bulk Data Access API. This is very similar to the rehospitalization example, with the exception that in this scenario, it may be important to be able to handle incremental data updates to avoid reprocessing huge amounts of data at high frequency. The FHIR Bulk Data Access API can be queried such that only resources that have been created or modified since a particular time are returned. An alternate way of bringing in data for applications such as our admissions forecast dashboard is to subscribe to changes and build features incrementally in real time. These features can potentially be used by dashboards and ad hoc analytic query, which may have requirements for more frequent update, or as a constantly updating source of features that can be sampled and used for training and monitoring models. FHIR subscriptions provides a way of informing a FHIR server that you wish to receive updates about changes that meet certain criteria. The FHIR server can call a REST hook to notify the client about a change. The client can take this update and push it onto a message queue, such as Kafka. Streaming analytic tools such as Apache Spark can consume a stream of events and run queries across them continuously. Pathling is a tool which enables the use of FHIR with Apache Spark, and it also supports the execution of SQL on FHIR view definitions. So A stream of features extracted from FHIR data using a SQL on FHIR view can be incrementally appended to tables in a feature store. These features can then be queried, sampled, and subjected to further feature engineering. Hopefully this has given you some ideas for designing FHIR-based solutions for decision support applications. To summarize, the FHIR family of standards offers a number of tools relevant to decision support, including bulk data access, CDS hooks, Smart App Launch, and SQL on FHIR. Investing in foundational FHIR interfaces for runtime and bulk data access may be a key enabler for supporting the deployment of decision support. We talked about several different patterns and use cases, including in-workflow clinical decision support, prompts based on a trained model. We also talked about the process of extracting data to train the model and how the model might be monitored post-deployment. Another pattern is that of operational decision support that provides guidance at a facility rather than patient level. We talked about different patterns for integration of this type of application, including batch data extracts and real-time streaming updates. Thanks very much for listening to my talk. I'd be happy to take any questions. Also, if you would like to leave feedback, you can do so using the DevDays feedback form through the QR code on screen.
Hi, great talk. So I have a question about CDS hooks in specific. So let's say a card gets displayed and the practitioner dismisses a particular card. And let's say the practitioner comes back into the same patient after a while. The same patient view gets triggered. So is there any particular standard around whether or not to display this card again to the same practitioner who saw this card?
My belief is that this is outside of the scope of the CDS hook specification, and there is all sorts of policy considerations around that. Like, for example, for some things, there might be a mandatory flow, like if it's more on the side of a clinical guideline or some sort of mandatory step which should not be dismissed. Other things might be a suggestion. You might want to record what came back, what was dismissed, the whole audit trail, but this really is outside of the part of it that's been standardized at this time, and it's really limited to here's a hook, and here are like a set of like results, suggestions, actions, smart apps to augment that, and then the EMR can sort of integrate that as they see fit, I think.